Good morning and welcome to the LCRIG hosted webinar for GAIST and TRL. My name is Emily Crane and I'm the Marketing Coordinator here at LCRIG, but I'm only here for the introduction. On the right hand side of the screen you will see a chat box. If you have any questions, please put them in there and we will have a Q&A session after the presentations. Now that I've gone through all the instructions, I'm going to hand you over to your first presenter, John Fletcher from TRL.
Hi everyone, thanks for giving us the time on your busy day on a Friday to listen to us talk about some things that we're involved with together. So, right, I'll just share. Okay, can someone tell me that they can see the screen?
Yeah, it's fine, John.
Yeah, good stuff. Right. So this presentation has been put together by TRL, but also with GAIST as well. We've been working together, particularly to do iRAP star rating work. So I'm going to introduce what iRAP star rating is, and then John from GAIST, two Johns, just to keep it simple. He's going to talk about some exciting things GAIST are doing, and TRL and GAIST have some really exciting plans brewing as well to extend this work in some pretty high-tech technological ways. So I'm John Fletcher. I'm head of practice in international safety, but I do a fair amount of UK road safety work as well. Go away. Right, a bit about iRAP star rating. So iRAP's a charitable foundation. They've got a base in Australia, but also here in the UK, actually in Bracknell, just up the road from TRL. So they've got a vision of a world free of high-risk roads, having a 3-star minimum standard for the star rating, and it's all about infrastructure, the standards of infrastructure, and they're active in well over 100 countries, so it's 100 countries and counting, and to date 1.5 million kilometers of road have been assessed by star rating. So TRL have been involved with iRAP star rating pretty much from the start. It started as something which was more about the roadside and reducing the severity of runoff crashes when they happened. So clearance and using restraint systems, and that was the road protection score. Now that developed and evolved into star rating models from V1 up to V3, which is the current model, and these are much more sophisticated beasts that do a lot more. TRL are the UK iRAP Centre of Excellence, and we've got a place in the Global Technical Committee which oversees the robustness of the iRAP models and protocols as well. So what is it all about? Well, frankly, there are some choices about how the road network can be developed, but in a lot of cases, road authorities are inheriting road networks which haven't really been designed in the UK in country areas, for example. But there are always choices, but unfortunately they cost money. So the model looks at things like what the risk is of having a ramped end on a restraint system as opposed to these better P4 systems that don't launch people into whatever it is you're trying to protect them from. And with restraint systems, you could have a wire rope system, the familiar metal barrier type, and on motorways in the medians, concrete barriers are used, and they've got different costs and different safety levels as well. So there's a whole load of things to juggle when you're deciding what to do with roads. So some of you will have these roads at the top here, country road. This is very high risk, but tends to have low volume. So you're limited to what you can invest in it, but iRAP can help you work out what you can do to upgrade this and make it less risky in a cost-effective way. Others of you will have dual carriageways, which have some features of motorways, but are not built to such a good standard. And then we've got high standard motorways and highways. Now you can put a lot of traffic through these, and because of the grade separated junctions, the shallowness of bends, good sight distances, and so on, these are very low risk. However, we've also got the situation where people actually feel happier on these roads, for example. So people aren't very good with risk, frankly. So the data from iRAP star rating is used for producing these maps, and these are very good at showing people who are less technical where the sort of risk areas are. So black and red are 1 and 2 star roads. You've got orange, yellow and green. You're aiming for green, you're aiming for 5 star as much as possible. These are the lowest risk roads. And I'm going to talk about safer roads investment plans. These are the actual schemes that the system comes up with, which are economically appraised. And they're a starting point for actually developing your road network into something that's safer. So the process is fairly simple when he said it out like this. It's not as simple in real life, but we need a GIS layer to define the network that is going to be star rated. We've done this for the National Highways Strategic Road Network a number of times. It's over 12,500 kilometres. We've got a whole lot of jobs that have just finished, or we're doing currently. So Transport for West Midlands, West Sussex and Surrey County Council, Isle of Man Government, Government of Wales, and we're working in India as well. Very active. And where GAIST come in big time is that you need good quality imagery of the road. You need a wide forward or better 360 imagery to be taken on a GPS instrumented vehicle so that you know where the image is from. And the great thing about the GAIST system is these go into servers that are then shared on the web, and they go into the coding tool that is used to actually characterize the road network in ways the iRAP star rating model can interpret. There are about 50 different measures, it's far too many to talk about here, which are coded up. So there's set ways to classify different road elements. These are all the elements that have an implication for risk and road safety. There's a coding tool interface used. We will do 10% checking of the coding that's done. It's largely manual at the moment, and we hope to change that so it is error prone. And here's a sort of typical coding tool. And so basically the person virtually drives along the route and then selects the different items when items actually in the screen along this line change. It's done to 10-meter accuracy, and then the worst thing in 100 meters actually makes it into the model. So we're gathering a lot of information about the road infrastructure that's present. This is just to show you the kind of tool in action. If you look on the right-hand side, you can see the codes changing as you virtually drive along the route. So that's picking up whether there's aggressive poles present, you know, the nature of the median, whether there's junctions or small accesses present, that kind of thing. So just to give you a little bit of how coding works in real life there. So what the model does is to work out the risk from the features of all these 50 or so infrastructure elements that road users are subjected to as they use the road. And the risk is a measure of your risk per kilometre driven, but it also works out where the killed and seriously injured should be occurring or will be occurring in relation to the traffic flow, but also the risk that's present and speeds as well. Now, this jumps around like crazy at 100-meter level, and it's actually useful for engineers and more technical people because you can dig into that. I'll show you that in a minute. But we also want to summarize this for less technical people as well. So this is another view. It's called a risk worm, and it breaks the risk, the total risk, down into different types. So the red or crimson is the intersection risk, and you tend to get spikes. I mean, junctions are not good for road safety. It'd be better if we didn't have them, but then the roads wouldn't work. So, well, there you go. Yellow is head-on loss of control. The green is runoff loss of control passenger side. And we've also got loss of control driver side. So what happens? So you've got an access here that might relate in this additional risk here. The head-on loss of control, because there's no physical median, that means vehicles could cross the center line there between the two lanes on the two carriageways. And then if this isn't frangible, for example, it's an aggressive object, and that will contribute to the runoff risk. So that is basically how iRAP works at a very simple level. But there's a load of algorithms behind generating this that take into account the risk, what we know about risk about different elements. And I said, it's handy to simplify, high risk and low risk longer stretches. So here, the average star rating risk is 3 star along here. And then this 3 kilometer section, actually the average along here comes out as being 2 star. And that generates these kind of maps here. So what use are these? So we can look at the pattern of risk for vehicle occupants, and also this is for bicyclists. And it also works out the risks for pedestrians and motorcyclists. So you can do things like use iRAP star rating to look into how you're trying to promote active travel, for example. But the thing that they frequently used for, or their kind of raison d'etre, if you like, is justifying investment in upgrading the network to make it safer for road users. This just summarizes the process. So we've got imagery there going into coding. We need to add speeds and flows. They're available from a number of sources these days. The crash data, Stats 19 data, needs to be processed to distribute fatalities and serious injuries across the network. We need the cost of lives and serious injuries saved, and that comes from the sort of DFT Green Book, and cost of the countermeasures. And with all that, you can do economic appraisal. So what the iRAP model can do is to actually model different infrastructure elements being tested in sections of road, and it economically appraises these. So what it will do is produce a list of suggested enhancements. Now, these are things which should be cost effective in the longer term. So it helps you as a road authority to identify safe system measures. It's different from doing kind of hotspots analysis or going by crash data history significantly. And it gives you a fair amount of information. So this is saying, well, this is all the places is suggesting shoulder rumble strips would be have a positive BCR, for example. And you get an overall idea of what the whole program, this Safer Roads Investment Plan, what the benefits would be, how many FSIs, fatal and serious injuries, are saved, total cost, the total cost of the benefits in people saved, and the benefit to cost ratio. So that I'll leave it there, and hopefully I haven't gone over time too much, and we'll bring John in.
Thank you, John, for the very clear description of the benefits of iRAP and how you use our imagery. Really useful.
Great.
So in terms of a little bit more about GAIST and our view and where things are going, we were established in 2007 and based in North Yorkshire. And as John explained, we primarily capture very high definition imagery. We've been the RAMS provider of choice since 2016, working with LCRIG and DFT. And as you might expect, we've collected millions of images, petabytes of data, and we serve that up, as John explained, via the cloud. And we also have 4 online tools that allow that to be used. And it is all georeferenced to OS Master Map topography. So each image and each frame is georeferenced and accessible in that way. So why do we do it? Well, it's quite simple. You know, old cities, new cities, all cities around the world use and rely on highways to thrive. And everything happens near or beside a road. So if you think about train stations, ports, harbours, coach stations, they're all linked to the highway. And the highway is the network, the economic network, but also the transport network for education, health services. So it's vitally important that that highway network operates as best it can and is as safe as possible. And that's where the TRL functionality comes in to enable that as well. So as I said, we take very, very detailed, high accurate images and produce simple to use, simple to understand, actionable insight. And that's built on the high definition imagery. So in terms of imagery, we have a 360-degree camera and also a road-facing camera, and we take 1,200 images per kilometre of highway. And that's a massive amount of reference data that can be used to extract data about the highway, the pavement, and all the assets as well. So we use a combination of AI and machine learning initially on the imagery to understand the defects. And we detect about 35 different defects in the carriageway, but also all the ironwork and all the features. And that includes the defects, and these are all georeferenced with areas. And what that allows us to do is produce a road condition map. And as we zoom in, you'll see that each area of the carriageway and the pavement highlights polygonized areas of similar defects. And each polygon references all the defect types for the pavement and for the carriageway. In addition, each area is also hyperlinked directly back to the imagery of that area. So you can actually physically see the defects as well as seeing the interpreted results. If we look at one of the services we offer, which is Safety View, what you can see on the screen is a small defect in October, in November expanded, and in January triggered a sufficient size for that highway to be eligible for repair and maintenance. And a patch repair was done, but unfortunately it wasn't done that well. And the month after started decaying, which actually led in April to a much larger area of the highway being requiring maintenance. So, as I said, in addition to the automated AI machine learning extraction, we also extract features, and that could be white line condition, that could be signage or assets by the highway. And for example, the signage is all coded to the DFT classifications already. So we have the ability to automatically extract, but if anybody tells you that AI and machine learning is the panacea and will deliver everything, it's not quite true. We still need manual validation, which is where the software that John has described gives that manual validation, but a bulk of the work can be done automated. And we also have manual validation at the end of our operations. So building on the view of safety, we've partnered with ASIN to be able to look at connected vehicle data, and that's their road trace data. And what that allows us to do is have insights about how vehicles are experiencing the highway, and in relation to safety, for example, where areas of harsh braking are occurring. And that gives us an opportunity to negate the causes and avoid incidents, the KSI stats that John referred to, before they happen. And that connected vehicle data gives you an insight into where to prioritize initial investigation. And if we look at the volumes and just take a snapshot from November, and this is just 45,000 vehicles, there were 15 million data points that needed looking at, and 870,000 of those related to harsh braking. And I hear that's too much data, so what? And it's the so what we're working with ASIN on. So we filter out events which would be expected. So in traffic jams at low speed, events on private property, car parks, events near traffic lights that aren't in a way with the metadata non-extreme, and also events in a similar vein by roundabouts. And then those are prioritized by frequency, average entry speed, and then also by the deceleration. So what was the delta in the speed? And that gives us hotspots. So we have a strong partnership to deliver complementary intelligence on top of the physical asset infrastructure and the breakdown by modal type, whether that be pedestrian, cyclist, car, HGV, etc. And that data provides an interim view from a yearly forensic survey. And you can still do the visual inspection using the imagery. So for us, that's data for change. And what we'll be doing is continuing to bring on more data sets that relate to the road, relate to safety, and provide this extra insight. So as a quick fly through and an overview of GAIST and what we do at GAIST, hopefully that's been of interest. Over to you, Emily.
Hi, it looks like we've got some questions in the chat box for you both.
Yes, I saw the first question related to the use of drones and whether drones could be used to augment the data collection. Current legislation for the use of drones in the UK is line of sight only operated by a trained operator. And the regulations currently state that drones could not be used over public spaces, and that includes highways. So at the moment, the use of drones to collect imagery on an active highway is not a possible solution.
Something that's being done in low and middle income countries is using satellite imagery to pick up some details, and it's not perfect, but that may, that may become more of a viable way to get some data in the future.
And the next question relates, how does GAIST compare to Vaisala? We both actively use imagery to assess. The method of collection is different in that we have 360-degree high definition cameras which provide the imagery that you've seen. As I understand it, the Vaisala unit uses a telephone within the cab to collect the imagery. And the outputs from those two devices differ. One requires post-processing hours, which is done overnight. So it's an automatic process where the data is downloaded after the drive, as where the Vaisala unit streams the data to a server and then can be used automatically. So the main differences, apart from we both use imagery, are the level of quality of the imagery, and then for us, the ability to extract the level of detail we do from our high definition imagery. Hopefully that answers your question regarding how GAIST compares to Vaisala. Do you have anything to add to that one, John?
No, not really. I think I've seen outputs from both the organisations, and yeah, I think there are interesting pros and cons, I guess.
Yes.
To what you do and what they do, for example.
So, and the next question is, how do we get length and area of distress from the AI? From a GAIST perspective, as I showed the AI analyzing each image, and we do take 1,200 per kilometre of highway, they're georeferenced. So the position and area, the area is detected by the AI and machine learning. The type of defect is also initially detected, and those are georeferenced based against the geography of the imagery and the positioning of the imagery. And we do have something called surface view, and what we do with surface view is take those angled images and convert them to a plan view and stitch them together. So you actually get a car-free view of the road surface with all the defects as well, georeferenced, and that's available as a GIS layer. And hopefully that answers that question.
Any questions about iRAP star rating while you have the chance?
So thank you very much for joining us, and especially for your questions. Hopefully you found both John and my presentation of use, and I'll hand over to Emily.
Thank you. I would like to thank you all for attending the webinar today. For further information on other webinars that we are running, please keep an eye on our weekly newsletter. Thank you all and enjoy the rest of your day.
Thank you all very much.
Thank you. And please feel free to contact us directly if you have any questions.
Absolutely. Bye-bye.
Bye-bye.